Thank you for hosting us. Cyrille here is the chief architect of the Fabriscale software, and I'm the product manager. I also serve as a professor at the University of Oslo. So we are happy to tell you about our experience with InfiniBand management and monitoring. We are a software company. We make software to make InfiniBand even greater. So that's our mission in HPC. So we are founded in 2004 by two researchers, Sven Arne Reinemo and Professor Tor Skeie. Both have worked for a very long time on routing in supercomputer interconnects. And the company is a spin-off from the university, backed by Simula Innovation and Norwegian and British investors. We have patented our solutions and are developing the technology from our headquarters in Oslo and have local support in the US and in Asia. Our vision is to move organizations using HPC from just buying equipment and focus on the nodes to actually manage the system that you already have and improve the performance of what you have. So we have two products, Hawkeye and Wingman. And with our products, you can monitor the traffic very efficiently. So you kind of get eyes into your system. You can see what's going on in your InfiniBand switches and in your InfiniBand NICs. And we also have optimized routing. It's a routing that better balance the network load and effectively can improve performance quite significantly. So we kind of have two views. One is inside the HPC system with our Wingman software. That's a subnet manager that really manage the software. It's the software that manage the interconnect, kind of replacing the OpenSM software. And it's a Hawkeye that's a monitoring tool. It's like a hunter's vision of your entire system, where alarms can be handled, where you can see the load in the network, and you can have rich analytics of your InfiniBand network. We also have historical data, so we store everything in a scalable database, so you can go back in time and see what happened when my job started to go a little slower. What was the difference? And you can troubleshoot your performance issues much easier. And Wingman is sort of watching your back. It's always listening, always managing, and it can improve the speed of your Mellanox network by doing faster routing, by having better balanced routing. We also do a trick that we pre-calculate everything that can go wrong. So in a large fabric, in a large supercomputer, there can be link failures, there can be switch down, power supply issues. There are things that can go wrong. So instead of waiting for something to go wrong and then doing a deep sweep, which takes down your network for a long time, we actually think what would happen. So in our subnet manager, we are preparing for the worst. So if a link goes down, we know exactly what to do, so we can reprogram all the switches immediately without any deep sweeps. So this can provide better reliability. We also are automating the use of virtual lanes. Many of you may know about virtual lanes in InfiniBand, but not everyone is using them. So we make it simpler to use virtual lanes. So you can envision that you have highways, and when there is a blocking, you can actually just take the next floor of the highway and make sure you have progress, even though there are queues happening along the first highway. We also have an interesting feature for security. For those of you that have multi-tenant setups where there are multiple projects running on the same computer, there are sometimes privacy requirements. And instead of setting that up manually, we have interfaced to Slurm so that it's possible that the Slurm job can automatically describe the InfiniBand partition. So you have a private space that is adapted for the job that you're running at the moment. And this is automated, so it can go quickly and with no user intervention. So a few words, I'll start talking about Wingman, and then Cyrille will tell about the monitoring system, Hawkeye, later with a demo. So just to tell you where we are focusing on FAT3 topologies. We are focusing on InfiniBand, and we are extending the current routing algorithms that's used by OpenSM by a Fabriscale routing algorithm. And I will show you a few performance benchmarks where we compare. Before I go into the performance, I'll tell you the sort of secret sauce, what we're doing. And to do that, I make an analogy about cars going from cities. So normally, and with OpenSM, every switch determines where the traffic should pass. So here in Oslo, packets are sent onwards to Fagernes and onwards to Geilo. That's 2 cities on the way to the destination Trondheim. But at Fagernes, that is a switch along the way. There is actually a long queue coming. It's a big traffic coming into this node. And the Oslo node has no way to know that. So what happens is that when traffic is merged, there's 3 cars from Oslo and the 4 cars from Fagernes, they are merged and actually creates a bottleneck, which affects the total performance. So instead, we gather information from all the nodes, and we use a powerful supervisor node that runs our software to get a view over the entire network. So then, because we will know that there is queue building up at Fagernes, we will send only 1 car this direction, and send all 5 cars to Geilo. And this actually results in a more balanced traffic situation in the entire network. So this is some of the secret sauce of our routing, that we make decisions based on global information. It's more processing intensive, but you actually have a lot of processing power in a supervisor node in an InfiniBand supercomputer. So then we can handle the situation that the road is closed. We can actually then do a rerouting with knowledge of all the routes. So we are using global information that gives us better balancing, giving faster communication. We pre-calculate redundant paths, so we actually simulate this road closure for a long time before it actually happens. Maybe it never happens, but if this link is down, we know exactly how to program the switches very quickly. And then we can also have robust routing, which handles irregular connectivity. And although if you read your InfiniBand user guide, you are told how to configure your supercomputer. Build a nice FAT3 topology, it says. Configure it this way. But in real life, customers tend to have failed nodes. Some nodes without power, some are rebooting at the moment, and it's actually not optimal regular FAT3 topology. And sometimes OpenSM has problems with that. We handle that. So also, as the network grows, this problem gets bigger. So if you have thousands of nodes, you have more probability of some errors, and we are prepared for that. So this is a performance comparison done at our home supercomputer at University of Oslo, where one of my colleagues at the mathematics department, he is expert in 3-dimensional fast Fourier transforms, very often used for simulations. And we ran his software on the supercomputer. It's 650 nodes, and using 56 gigabit FDR. And we were actually able, when we were using 16 cores per processor, we could show a 41% application speed increase when we were running our subnet manager compared to the open source subnet manager. This is partly due to a large blocking factor in this computer and not optimal topology, but we have found, talking to several customers in the US and Asia, that many computers have non-optimal configuration, and real life is not always as nice as is in the installation instructions for your Mellanox switch. So you see that the benefit decrease when you have less nodes and less cores, and that is because when you have only one core that's sort of feeding the network with traffic, it's not so much congestion. But as we heard from the Intel presentation, that you're having was it 72 cores per CPU in the near future, then of course it's a lot of traffic push that goes into each NIC, and then this situation worsens, and then we can help more. We also did an interesting test in Asia on a computer with 122 compute nodes, and this was with EDR and with 32 cores on every computer, and we used the DK Pandas OSU benchmark, all-to-all. And we found that actually as a function of the packet size in the test, we could show that the percentage improvement came all the way up to 40% when the when the packet size was increasing. So at that packet size, a bottleneck was created, and we could sustain the traffic better. So this is also application level performance. So we see that when there is traffic congestion, we can really help with better routing. We also did a comparison with a larger computer, 648 nodes. Here, unfortunately, we do not show much speed improvement when everything is okay. We're actually running with one virtual lane. That is the red results. We are running in the exact same performance as the open source OpenSM. However, if we utilize the multiple virtual lanes, we are a little faster. But the interesting comes when there are some faults in the network, because when some links are down, actually the FAT tree is no longer balanced, because what we are using here is a perfectly balanced FAT tree, and then we can't, then OpenSM is actually as good as what we are. But when there are some errors, some nodes are down, some links are down, and the tree is no longer perfectly balanced, we are significantly outperforming the open source version. So in this case, it's 3% faults, and all nodes are fed with 10 gigabit per second traffic, which is far less than the 100 gigabit capacity. We see that we can have significant speed up in this situation. And if we go to the sort of real world, we are using here some customer computers that we are currently installed on. And there we see also in the situation of no faults, we see a great improvement in performance, both with when we use a single virtual lane, and when we use 8 virtual lanes, we have even more significant improvement. Also in the situation where we have no faults. This is a cluster with the 96 nodes, so it's a fairly small HPC computer, but still able to show performance speed up. When faults are introduced, we also have the same behavior. A slightly bigger machine, 1,600 nodes, that actually is a very bad configuration, but this is a real computer used by one of our customers. And the reason why it's extremely poor performance here is that for certain non-optimal FAT tree configuration, OpenSM are defaulting to min-hop routing. Of course, that's not a fair comparison. But actually, we are running on the same topology, doing the same automated processing, and we are able, by smarter routing, to actually run full FAT tree routing, even in this non-optimal topology. So this helped us a lot because the customer installed just a new subnet manager and got like several 100% improvement in performance when no faults were registered. And we were, of course, very happy to show that. But we are we have experienced that in real life this sometimes happens because customers are not always configuring the InfiniBand networks correctly. Then a few words about our reliability performance. So, as I mentioned, when we turn on our subnet manager, we calculate all the potential errors that could happen. Any switch down, any link down, and prepare for that. So when there is a problem, normal InfiniBand initiate a deep sweep, but we don't have to do it because we are prepared. We know from the interrupt which link went down or which switch was no longer reachable, so we can deduce what was the problem and immediately program the involved switches to go around the problem. So we can maintain connectivity. And there you can see we have only 4 milliseconds to reconfigure a 324 node network. And that is much, much faster than OpenSM, which needs several hundred milliseconds. And of course, as the complexity of the HPC system grows, let's say to 648, 5,000 or even 11,000 nodes, we are still in the millisecond range, while OpenSM is in several minutes. So I noted that some previous talker talked about deep sweeps interrupting file transfer, file I/O. Here we would be very quick to reconfigure so that the application level would not even see it. So just to summarize, Wingman is a new subnet manager that is optimized, as optimized routing, can take some strange configuration, which we have found to be happening in real-life computers. We have this dynamic fault tolerance, which enables very fast reconfiguration with sub-second rerouting in case of failures. And then there's dynamic and secure InfiniBand partitioning. So that's automated and integrated with Slurm. And we find this particularly interested for multi-tenant HPC systems, let's say public HPC systems that has several workloads that should not be allowed to talk to each other. And then Hawkeye, which is our network monitoring system that has a new modern user interface, no longer telnet into your favorite Mellanox switch, but get nice topology view and component navigation, and integration with Slurm. But this monitoring system is much better to see than me talking, so I'll introduce to Cyrille to do a quick demo. He's actually put a complete supercomputer inside his laptop. So then, yeah, I think you could take over from here.
1, 2, yes. So as Haakon said, so we have the monitoring system that will give you some insight on your InfiniBand cluster. We have full access to all the metrics and information about the various InfiniBand ports from our subnet managers. And then we also have some integration with workload manager so that we can pull metrics from the workload manager. And then we combine the network topology with the various information from the workload managers, such as giving a view of, for each job, what kind of port will be used, what kind of server will be used, and trace the route taken by all the potential compute nodes from this particular job. But first we have some slides, and then I will do a live demo. So, Hawkeye, our monitoring system, is based on the plugin architecture. So, when we say plugin, it means that we have some backends that will receive various source of information from various plugins that we have written. This backend will collect all this information and will map ports, nodes, and servers for being visualized in the topology. We have already written 3 plugins. One will be to get information from the Slurm workload managers. So we support Slurm 16, 17, and 18 versions. We have also written a Torque version of the plugin to get information from PBS Torque. We have also written a plugin for adaptive computing, Moab. And we also collect information from our subnet managers to get metrics from the InfiniBand ports. All the metrics are stored in Elasticsearch, search engine. The reason is that we would like to be able to do aggregation on those metrics. We can also run a lot of the kind of jobs on that, so that we can get analytic results from those data. We also store the topology of the network, so that we can map and get the routing tables and so on, so that we can map and trace the path taken from one compute node to another compute node, so that we can visualize the traffic across compute nodes on the entire network. Then we provide API to access all those data, or both the detail, the topology, and all the metrics. We provide an API so that we can access to all data. This API will be used by our dashboard, but can also be used by external monitoring system or by scripts that you would like to write to get more insight in your network. So, what kind of analysis we can do? We can check for congestion in the network. We can see and visualize long-term utilization of the traffic across the network. And we can also tailor the monitoring for a particular job or particular failures on the network. We will be alerted when there is a link failure or port failure in the InfiniBand network. So that will raise an alarm, an alert in the system, and then we can visualize and quickly see the alert. We can also visualize the state of the network from the job scheduler point of view, so that we can see all the nodes that are idle or allocated for jobs. And then we can have our own alert system, so that we can, the user can set threshold on particular counters, like error counters or data counters, and then we can raise alerts so that we can be notified for particular errors or irregularities in this cluster. And then we have nice visualization so that we can get report and so on. So now it's time for live demo. That's the tricky part. So this is our main dashboard. So a few words about what we are going to visualize here. So on my laptop, I have a simulation of the InfiniBand cluster that contains 324 nodes, and it's a 2-level FAT3 InfiniBand cluster. So we run a simulation of the InfiniBand cluster using libsim tool. Then we run our subnet manager. We run a simulation of a Slurm workload manager that is connected to the subnet manager, so that it will reflect. So when there is a new job that is simulated, it will also trigger some traffic. So everything here just run on my computer. So we have also the Elasticsearch database running on my laptop, and so on. So as you can see, here we have some running jobs. So we have some running jobs, we have some network activity, and some system activity. So the network activity that we display is actually the, in percentage, the current throughput compared to the maximum theoretical throughput of the InfiniBand port for all the nodes in the cluster. Then we have the system load, which is as reported by the workload manager. In this case, that will be Slurm, that reports the Linux system load for each compute node. And then we have the number of cores, and then we deduce the metrics from that. So we have an idea on how loaded in terms of CPU the system is at the current time. And then we can display also the number of pending jobs and running jobs in this cluster. And then we have the historical view of those metrics for the latest 15 minutes, but we can also go back up to 30 days. So all the metrics are stored and can be retrieved from our Elasticsearch instance. On the right side, you see the counters here. That will display your view on the InfiniBand cluster, so the number of active ports, ports that are not connected, and the ports that are done in the system. So far, everything good, no ports that are done. And At the bottom, we can see and visualize the number of servers or compute nodes as seen by the workload managers. And here we see that we have a total of 230 nodes that are active and are actually processing a job. And we have some idle jobs, so compute nodes that are not that don't have any jobs to run yet. So we can load a little bit more the. So I'm going to run a simulation and make more jobs so that we have more network activity and more jobs activity here. But that will give you an overview of the system. We have another view here that will represent all the jobs that are in the system. We can also just show the running jobs, let's say, and then we see what kind of jobs are running at the moment in the system. What is important is that, so we display like the most important information that we think are important for the admin point of view. So we have the jobs, and we have the list of compute nodes where this job is allocated. If we click Show in topology, we can actually visualize the allocated jobs in highlights. They are highlighted, and you can see the ports and the switches that are involved in the traffic. All the other green computers, they are allocated compute nodes, so they are running jobs. We have a similar topology view. If you would like to go and search for a particular server or a port or switch, then you can also do a search, and then you can search by UID or server name and so on, and then you will get the various information here. So if we, let's say, take a particular switch, and then we have all the ports for this particular switch, then we can see how it is connected to. So we can see that the switch 0 is connected to switch 9 from port 1 to port 19. And then we can see the details. Here we will visualize the traffic received and transmitted across this port, this InfiniBand port. We will also display the number of packets sent during an interval of time. And then we can also deduce the average packet size so that we can have an indication on how this particular InfiniBand port is saturated or not. And on the right side, we display all the information returned by the InfiniBand port. So various details like LID, UID, and so on, and also the error counters. And because we have integration with the workload managers, we can also display what contributes to the network activity for this particular port. So here it's a switch 0, so it's the traffic visualized for a switch port. So because we know we have the map of the entire, we know all the jobs that are running on the system, so we can track what traffic can come across these ports by looking at all the jobs. So right now we see that there is only one job that can contribute to the traffic, and it's because it's running on compute node 0, 185, and 4. And probably compute node 0 is attached to switch 0. So from the component view, we can go through InfiniBand network traffic to jobs and vice versa. We like to have a bird eye on your activity in this cluster. Then all the links are colored by networked activity so far. And then from green to red, then you can see the load across the links. So this is here a pure simulation, so those actual numbers don't represent anything. It's just to see some example of load that are links that are heavily loaded and links that have no traffic at all. And then you can see that here you have compute nodes that are in green state because they are running actual jobs. You have the switches, and then you have the links between compute node and switch. And then here you have the root switches, and then you can see and visualize the links activity. So this dashboard is in this 1.4 version. It's the foundation, and then later on we can also visualize in this topology other kind of metrics, probably like congestions or errors and things like that. Yes, so the interactive part is going to actually simulate a link failure across the network. So I'm going to run a script. So I'm going to randomly disconnect a switch-to-switch link. So it's going to tell ipsim just to turn off one of the ports. So we have disconnected a link. And then you can see now that we have one alert telling you that a link has been disconnected. And it will tell you which switch and which port. So here we have the switch 4 port 11 to switch 19 port 27 disconnected. So that will give the operator or the system administrator instant alert that there was a problem in this network. And then you can see the traffic, and then you can take action, and then you can see that here the link is done. So you will get no traffic here. You don't get any traffic now. We have a simple acknowledgement and postpone action that we can say, okay, I have seen this alert. I don't have time to take care of that now, but I will just mark it as postpone, or I will acknowledge it. And I will do an action later. So when the link failure has been repaired, so if we have re-enabled the port or change the cable and so on, we can see that the alert will disappear. So I'm going to reconnect. So I'm going to reconnect the link that has failed, and now the alert is gone. So let's do another disconnection. Link are also visualized in this topology. So if I just hide link performance, it should be here, yes. Then you can see that the link that has failed is this one, between switch 8 and switch 14. So that gives you an immediate indication that there was a link failure in this topology. We also have a performance view, so we just highlight the top 5 senders and receivers, so that would be the top, the list of the 5 ports that will transmit or receive the most traffic across. We have also the number of jobs that have the most, that use the most of the compute nodes in the system. And we can also highlight links by congestions or link error and so on. So right now we say that we are building the dashboard. We have this version, and then we can complete and add more and more metrics, and we can also add more and more diagrams, plot, and charts. Jobs, yes. For the alerts, right now we have a link disconnection, but we can also configure the alert system to have a list of all potential counters that we would like to track and raise an alert if they are over a certain threshold. So here, for instance, we have all the error counters as reported by the Infiniment ports, but we can also add counters from Slurm or from like system load and so on, so that if a node is overloaded in terms of system or bandwidth and so on, we can raise an alert. So we can just pick up any counters, select an operator like greater or lower, and then raise an alert with some kind of criticality. And as I said, we have a plugin architecture. So right now we are doing the foundation. We have the 1.4 version ready. And then we can add more plugins. So one instance is that we can add plugins for more kind of workload managers like LFS, but we can also add plugins for the file system. So we have requests. We had received some requests from potential customers to have support for Lustre cluster or for BFS clusters. So we can potentially add more and more metrics to the system. And our design will match. So we can map network traffic, let's say, across the different file system. So right now we are focusing on the workload management point of view, but if we add file system, then we can see the jobs that are run by the file system, and then we can see the traffic across the InfiniBand ports. Yes, but that's it. Thank you. So this is live demo for over.
As you see, we have smart software that makes your InfiniBand hardware simpler to use and run faster. So we think that many system operators could leverage this. Maybe use to telnet into Mellanox switches and write Perl scripts to process data. That works, of course, but you might have something more fun to do. So instead, let us do this job and give you the oversight and also increase performance by smarter routing and increase reliability by pre-processing everything that could go wrong. Because in a large system, there are nodes that go down from time to time or links that it's replacing cables. Here you get help to do it.
And with the monitoring system, we can see immediately when there is such kind of alerts. Because if you have like a batch script that will run every day just to check all the InfiniBand ports and so on, that will probably take you some time to realize that there was a failure in the system. But here you can see that very quickly.
So finally, we have an offer to you. If you are interested, we'll come to your site, install it for free, and show it on your computer. So that's if someone is interested, then give me a call.
Stop selling. You're over.
Thank you.
Thank you.